We'll now look at another method for doing approximate integration. It helps to briefly recap what we know so far. So our first method was to slice up into n pieces and use either the right-hand endpoint or the left-hand endpoint or a midpoint to figure out what the height of the ith slice is in order to approximate it by a rectangle. So our picture looks something like this. And the more rectangles we took, the better the approximation got. Now, the key here is to notice that on our particular slice, we chose to take a rectangle as an approximation. So in some sense, we just capped off the slice by a horizontal line. And the variations we have between right-hand endpoints, left-hand endpoints, and midpoints were just choices in how high to take that horizontal line to cap off that slice. Now our next technique was to then use a trapezoid. And in some sense we can think of it as just, well, for that particular slice, rather than take a horizontal line and use a rectangle to approximate the area of the slice, we chose to join the two endpoints by a straight line. But in both of these cases we're still using lines. Either horizontal lines or lines through the two endpoints. We're still using lines. Now maybe the next level in doing the approximation would be to choose something more complicated than a line to cap the top of the slice off. And in some sense, lines are just polynomials of degree 1, so maybe we should look at capping it off with a polynomial of degree 2, or a quadratic. And that's what Simpson's rule is. Simpson's rule says, take two slices together, that gives you 3 points. 3 points define a unique quadratic, a unique parabola. So cap off two of the slices joined together, cap them off by a parabola that passes through the 3 points of those slices. The left-hand endpoint of the first slice, the right-hand endpoint of the first slice, which also is the left-hand endpoint of the second slice, and the right-hand endpoint of the second slice. So in order to do this, we need to know what the area is under a parabola over an interval. But this isn't so bad at all, because this is just integrating x squared, which we know to be 1/3 x cubed. And it turns out that the formula that we get by using these parabolas to cap off the slices is quite straightforward and very similar to the one we got with the trapezoid rule. So again, let's just recap what we just discussed. We're going to take our curve, slice it up into an even number of slices, because we're going to join two slices together. So for any two slices, we're going to look at the points corresponding to the x values of those slices, the endpoints of the intervals, and we're going to connect them by the unique parabola that passes through all three of those points. And that's going to give us a way to approximate the area on that slice. So the area under f from xi minus 1 to xi plus 1 is approximately then the area under the parabola through the points pi minus 1, pi, and pi plus 1. So we sum over all of the areas of the parabolas. Now the details of this are in the text, and I encourage you to read it, but it turns out that it's quite interesting. When you want to compute the area under the parabola passing through 3 points, it's certainly related to the width of the interval that you're using, and it's related to the heights of the 3 points you've chosen, but it turns out it's related to the height in such a way that it uses the height of the two endpoints once, and it uses the height of the middle point 4 times. And that's interesting, because when we look at the rule then, which is known as Simpson's rule, the integral from a to b of f of x dx is given by this sum, where we're sampling the heights at all of these endpoints of the intervals. It uses the left-hand endpoint once, it uses the middle point, which is obtained by joining the first two intervals together, it uses that 4 times, and then it uses the right-hand endpoint once. But it'll use that right-hand endpoint once again in consideration of the next interval. So we get this pattern that happens. We get this pattern of 1, 4, 2, 4, 2, 4, 2, 4, and then back to 1 again. And again, the details of this pattern and why it occurs are in the text, so please read that. But I just wanted to point out to you that the reason that it's coming out is when you compute the area under a parabola through 3 points, it uses the height of the endpoints once and the height of the midpoint 4 times. And so since these endpoints are being used twice in terms of the intervals on either side of them, that's where these 2's are coming from. These 2's are because those heights are being used in both parabolas, one to the left and one to the right. The 4's are coming straight from the fact that it's one of these middle points in the parabola, and they get counted 4 times when computing the area. So again, read the textbook, see the details of this calculation, but this turns out to be the formula for Simpson's rule. So let's have a look at an example then. So we're going to approximate the integral from 0 to 3 of 1 over 1 plus x to the 4th by Simpson's rule with n equals 6. Let's first get a rough sketch of this. 1 over 1 plus x to the 4th's got to be decreasing, passes through 1 and then starts to come down. And it's symmetric, so it does the same thing on the other side, but we don't need to worry too much about that because we're only interested on the interval 0 to 3. And then our slices look like this. And what we're interested in doing is joining 2 of the slices together, say the first 2, and throwing a parabola between those points, and then finding the area under that parabola, and so on all the way along. And this is the formula then we're going to need to apply. So we're going to need to know what each of the xi's are all the way along, and then the corresponding function values at those points. We have the xi's. So the Simpson's rule approximation using n slices is delta x over 3. Delta x is 0.5. And then it's this pattern of 1, 4, 2, 4, 2, 4, 2, 4, 2, 4, all the way along until you get to the end of the number of slices you have, in which case the last one just has a weight of 1 on it. So which becomes this when we plug in the xi values. We get a value of approximately 1.109030978.5. Okay, again, one thing to keep in mind is with these approximations, we're going to need to add up a bunch of numbers. Now, I don't want you spending time plugging these things onto your calculator. That's not a good use of your time. You want to understand what the process is, how these ideas are coming together, what the formulas are for coming up with these approximations, but the actual carrying out of the arithmetic is not so enlightening and a rather poor use of one's time if you're plugging it away on a calculator. So use a computer to do this. You can write a little piece of code to get it to add up these numbers. You can use Wolfram Alpha, or you can use the code that I've already given you online. So if you click on the link that I've provided you in the lecture schedule on WebCT, it brings you to this site, and you can read the URL off from the top of the browser. And here I've got all of the code implemented for doing all these different approximations: midpoint rule, trapezoid rule, left and rights, and Simpson's rule. So if you click on the Simpson's rule, it takes you to the very bottom of the page where there's an implementation. A brief reminder of what Simpson's rule is in terms of the pattern for the sum that you get. And then the little code block has a definition of the function Simpson's rule. So this is how it's being defined in this little script window. It takes as an input a function, an interval a to b, and n, which is the number of slices you're going to use. And for Simpson's rule, this better be even because we have to pair up every 2 intervals together so that we can cap it off with a parabola. We've already set up the problem. We're just getting the calculations done by a computer, which is a good use of our time. So let's go ahead and change the individual example for our needs. So n equals 6, well, that's still the same. The function we changed to 1 over 1 plus x to the 4. And the interval we changed from 0 to 3. And now we hit evaluate. And right below it, we'll come out with a value of this approximation using Simpson's rule with n equals 6. Now notice here, it's no more difficult to then bump up that number, use more slices. So maybe we'll use 20. And we see that we get another approximation, and this time using 20 slices. Imagine trying to do this on your calculator. Not a good use of your time. Now we've got this thing implemented. We could go ahead and compute this using 2,000 slices. And it comes back very quickly. So you can use this to explore some of the other examples that you're working on as well. So one of the things you might ask now at this point is, okay, we've done with n equals 6, we did it with n equals 20, we did it with n equals 2,000. We get these values out for the approximations. How good are they? How good are these approximations to the actual value of the integral? We don't know the actual value of the integral. That's the whole reason we're using these approximations. But we'd like to know, once we get an approximation back, how good is that approximation? Do I know it hits the first 4 decimal places or 5 decimal places of the answer? Do I know how close it is? What the error is between it and the actual answer? Because if I don't know that, then using Simpson's rule with n equals 2,000 to get this approximation, I have no idea how good that is. I don't know if I should go actually to 4,000, n equals 4,000 to get a better one. I don't know if this one actually hits the first 9 decimal places or 10 decimal places. So how can we actually figure this out? How do we figure out how big we need to take n in order to get within some specified value of the actual value of the integral? Well, just like the midpoint and trapezoid rules, we have bounds on the errors between the actual value of the integral and what Simpson's rule is returning. And in this case, the size of the error bound depends on the fourth derivative of the function f. And so here is the statement of the error bound. If we know how big the fourth derivative of the integrand is on the interval ab, then the error in using Simpson's rule is given by k times b minus a to the 5th power over 180 times n to the 4th. So let's see how we can actually use this. Here we want to approximate the integral from 1 to 2 of 1 over x dx. And we want our approximation, when we use Simpson's rule, to be accurate to within 0.0001. So we need to come up with the n value ourselves. So let's go to work on what the bound is. The bound depends on the fourth derivative of our integrand. So let's work out what the fourth derivative is. Now we need to figure out how big this fourth derivative is. Well, here we just notice that the fourth derivative is a decreasing function on the interval 1 to 2. So the biggest the absolute value of it could be is obtained by its value at the left-hand endpoint, and this is 24. Now we want the error to be smaller than 0.0001, or in other words 10 to the negative 4. And so it suffices to choose n so that k times b minus a to the 5th power over 180 n to the 4th is smaller than 10 to the negative 4. And now let's plug all our information in. And so rearranging, we get that n to the 4th has to be greater than 10,000 times 24 over 180. And this means then that n has to be greater than or equal to the 4th root of this, which is approximately 6.04275. So n better be bigger than something a little bit bigger than 6. But remember, n also has to be even. So n has to be bigger than or equal to 8. Because that's the next even number after 6. So if we take Simpson's rule with n equals 8, we're guaranteed to get our approximation of the integral accurate to within 10 to the negative 4. So in particular, we get s sub 8 is approximately 0.69315, etc. And we use the website to do this calculation that I just showed you. And we know that the actual value of the integral, this number plus 0.0001, and at least this number minus 0.0001. So we know the integral is between these two numbers, from which we can conclude that we've got at least the first 3 decimal places of the integral. So we know that the integral is 0.693. We just don't know what follows after that. It is interesting to note that we could do this comparison with the trapezoid and the midpoint rule. And to get this same error, if we were to use the trapezoid rule, we'd need to take n at least 29 to be guaranteed we're within that error. If we're using the midpoint rule, we need to take n to be at least 41 to make sure we were within that error. So Simpson's rule seemed to have done quite good because we only needed to slice it up into 8 slices. That's it for this section. Thank you for watching.